Uh, Good afternoon, dear professors. First of all, I would like to thank you to organize this research seminar. And for me, it's an honor to give a talk in this seminar. And today I'm going to speak about the minimal energy for geometrically nonlinear elastic inclusions. And this is joint work with Martin Kruzik, Hans Knüpfer, and Ankana Roland. And this work has been done when I was in Heidelberg as a postdoc. Here we consider the sum of interfacial and the elastic energy. The first integral is interfacial energy, whereas the second integral is elastic energy. And here chi encodes the location of the new and minority phase that's described by F and V. And if we want to be more precise, we consider our integral on the following admissible set, which we denote with AM, and this is chi V. Chi is from bounded variation set, and while V is H1 log. So this means that nabla V should be in L2 space. And fuzzy V is a bi-Lipschitz with a constant M. So that means that Lipschitz V itself is a Lipschitz with constant M bigger than 1, and its also inverse is a Lipschitz continuous with M, and fuzzy V is homomorphism. While nabla, the first interfacial energy is nabla chi is equals to the supremum of the chi divergence V dx, and V is from this space C1 C1 locally, and then while and maximum phi x is smaller than 1. And SO2 means, geometrically, it means just rotation set. Okay, if we, to just give a short example about this, if we consider just,
Sorry, just a second. I'd like to check this integral or this is так, two unknown functions here. That's ch and he and nu.
yes,
Nu or v,
chi
v, v,
and
yeah?
V.
Chi and v.
Yes.
The chi is between 0 and 1. The
Chi maps
locations of the
R2 to 0, 1. This is like a characteristic function.
yes,
Mhm.
but it's a smooth function, no?
Uh,
Usually a characteristic function is not smooth. Yes, it's not
not
continuous.
smooth. Yeah, it's not smooth, but it should
Is
have
it,
some regular. For example, it can be in R2, it could be
it takes only two
rectangular.
values, not 0, 1. It's not interval. It's only 2 points. Yeah, 0 and 1.
Yes, it's 2 points.
It's yes, it's not continuous. It's definitely yeah. And wine minus here. What does it mean? Gradient chi. If
Gradient,
chi is not continuous.
this we define in a distribution sense.
In the distribution sense.
Yes.
Yeah, no, for example, if it's a Dirichlet function, it's just 0, yeah?
Uh-huh.
For example,
Yes.
uh, in the
And
distribution sense, it means chi is defined almost everywhere, not at each point. It's not necessary to be defined at each point because it's a regular distribution, not singular. It means that it may change the values on every set with zero measure. Yeah, include the location. Yeah, it's clear. And V is a smooth function.
Yes.
Uh, it must have only first derivatives. It's enough, yeah, to define
Yeah,
this
first
integral.
derivative in L2, I mean, it should be
Uh,
derivative L2
the
square.
distant square. What distant between what gradient V and SO2? What does it mean?
Yeah, this is SO2 is rotation, and then the square
The
distance
square
from nabla
distance
V
from
to
is
SO2 is
minimum.
minimum R from SO2 nabla V minus R. And here this modulus means Frobenius norm.
Just a second again. V is a matrix.
V is a vector. It maps
Vector.
to R2 to
Gradient V
R2.
is a matrix.
Yes, yes, correct.
Uh, uh, 2 times 2 matrix.
Yes, yes, correct.
Yeah, and in SO2, you are looking for the matrix which is as near as possible to gradient V. Is that? That is distance. Distance square. No, it doesn't.
Yes.
Distance square, it's distant square because it's a minimum. What does it mean? Modulus gradient V minus R. What's the meaning of that?
Uh, this is
All the
Frobenius norm.
squares. Sum
Yes.
of all squares. Yeah, it's a Euclidean norm. Yeah, in SO2. It's not operator norm.
Yeah, it's called the Frobenius norm.
Frobenius? No.
Yeah, Frobenius is like a square of all of them, and
Yeah, usually I have heard that it's Euclidean. It doesn't matter. Yeah,
uh,
all these norms are equivalent. Yeah,
yes, yes,
because
yes.
it's finite dimensional.
Uh-huh.
We assume that there is given mu such that chi must satisfy.
We assume that there is a mu also such that chi must satisfy. I mean, which is the volume of this thing is equals to mu, and for the region M, X in R, this is like a associated with a minority phase.
What that means that there is a given mu. If chi is measurable, mu exists. Any case, it exists. Yeah,
Uh,
just as this integral. That's all. Uh,
yeah, it's just the integral of mu. For example, if we take as a
it
chi
means that this measure m
rectangle.
is finite. That's all. No, the measure of m capital is finite.
Yes, yes,
It's the same.
yes, yes, of course. Because if this is just a measure of m is equals to
Mu and
mu.
m capital is the same. It equals to m capital or no?
A
It's
measure
the
of
same.
yes,
No.
yes, the same.
Number mu and number m capital, they are equal.
M is a set, while mu is just a number.
M is a set, yeah, and mu is
Yes,
measure.
yes.
Yeah, okay.
And it's
I
yeah,
decided
it's
that
like a
M is measure too. M is just a set, yeah, set.
yes,
Mu is the measure of the M capital.
yes, yes, correct.
And previous slide again, please. Так, nice. Integral on the top is understandable. Так, AM, our energy on the following admissible set. AM is a set chi and V. Так, what does it mean? The B, V. V is the finite variable, no? No,
This is bounded variation.
bounded variation. Yeah,
Yes.
usually, yeah, usually they use one V. It's enough. Yeah, variation, bounded variation. Так, R2, 0, 1. Yeah, multiplied times IH log, IH log R2, R2. V is by Lipschitz. What does it mean by Lipschitz?
By Lipschitz means it's Lipschitz continuous with constant m bigger than 1, and its inverse also Lipschitz constant continues with m bigger than 1. I mean, both of them has
What this is Lipschitz constant m. What
yes,
what does
because
it mean m? What's the
m is
meaning of m?
in the Lipschitz continuous function, there's a constant which is called L.
In Lipschitz condition, there are two constants. One is a exponent, and another is coefficient. It's coefficient, no?
Uh,
From one point, the distance from one point to another in the power alpha, no? Or one.
Power is 1.
Power one. It's a Lipschitz one.
Yes,
Usually,
yes,
Lipschitz alpha, there is such a no as
yes,
Lipschitz. And m is a constant. Uh,
yes.
but if the constant m is less than 1, it's the same as with constant m greater than 1, no difference.
We can take a maximum of it. Therefore, I mean, as a Lipschitz constant, if m is smaller than 1, we can choose as a bigger m because we want m to be
It's
the
without
same.
any questions, yeah. If you have some Lipschitz constant, any constant which is greater than 1 is a Lipschitz constant too.
Yes, yes. Right.
Yeah, is it necessary to write that m is to this is condition m greater than 1? Just m, there is exists the m. You every time you can say that m is greater than 1 or greater than 2. It's up to you.
Yes, right.
Or you need the special case that m is greater than 1.
Because it will be used when we look at the inverse of it. I mean, in one lemma. Therefore, we just want it to be m to be bigger than 1. I mean, our
You think that inverse map has the Lipschitz constant greater than less than 1?
I mean, we can always choose. I mean, it will be bigger than 1. I mean, it will be bigger than 1, but our like
This
minimization.
condition, V is by Lipschitz with constant m is greater than 1. This condition is absolutely useless, I think. Because if there is any kind of, if V is by Lipschitz, that's all. Every time you can choose the constant greater than 1. It's not special condition.
Right, yeah. Yes, you are right.
You cannot give me example of the V function V, which is by Lipschitz, but not with the constant greater than 1. You cannot give this example because every time you can change this constant by another, that's all. No?
Yes, yes.
Okay, please continue.
Шавкат Арджан, I think, я думаю, если обе функции, обе, v and v minus 1 is Lipschitz constant, then cannot be less than 1. Oh, yes, okay.
Сейчас.
Обе,
Какие обе функции?
v and v обратный тоже Lipschitz constant. Обе должны быть the same. M.
Сейчас.
Поэтому
By Lipschitz with the constant means that V is homeomorphism and V and Lipschitz continuous function with Lipschitz constant M greater than 1.
Она не может быть меньше единицы, да?
Нет. Я теперь понял. Вот здесь как-то так написано туманно.
Да.
Нет, здесь другой смысл. Надо, чтобы отображение V и обратное отображение имело одинаковый константу Липшица.
Да. Поэтому не может быть меньше единицы.
Чтобы у них была одинаковая константа Липшица. То есть, если V имеет константу Липшица M1, а обратно имеет константу Липшица M2, необходимо, чтобы M1 и M2 были... Нет, M1 равнялось M2, да?
Да.
И было больше равно единице.
Да, поэтому не может быть меньше единицы, да?
Сейчас. Почему не...
Наверное, всегда можно выбрать две константы, которые будут равны достаточно
Конечно.
большим.
Нет, я вот что-то не могу понять. Вот сейчас вот совершенно верно, Аслан Владимирович. Вот, допустим, В имеет константу Липшица М1.
Да.
Какая-то, неважно.
Ага.
А обратно имеет константу Липшица М2.
Да, да.
Тоже неважно. Вот. Теперь возьмем любое число больше, чем М1, М2 и единицы. Оно будет и константой Липшица у В, и константой Липшица у обратного отображения, и будет
Да.
больше единицы. То есть вы не приведете пример отображения, которое будет Липшицевым, но чтобы у него константа не была больше единицы. Всегда можно ее выбрать больше единиц. Или здесь какой-то другой
Нет,
глубокий
и
смысл.
хотя бы одно из констант М1, М2 будет больше единицы, не меньше единицы, да?
Ведь константа Липшица чем меньше, тем лучше, правильно? А вы видите больше единицы. А я kadar konstanta Lipschitz bulsa ondan katta bu boshqa ixtiyoriy konstanta u ham Lipschitz konstanta bo'ladi.
Нет,
Нет?
само отображение и его обратный тоже имеет одинаковый, хотя бы одна из них больше единицы, да, констант.
Нет, здесь ничего, по-моему, вообще, может быть, какой-то другой смысл. Если как вот сказали, тогда ничего, что им больше единицы не нужно, зачем? Ну ладно, надо смотреть доказательства.
Ага.
Потому что так, здесь что-то есть, какой-то смысл есть, но трудно его уловить. Если бы это было вот как, смотрите-ка, ну там в другую сторону неравенство. Да, там, если бы это в обратном, когда равенство, если бы равенство, то там нет неравенства. Нет, не видно. Это не показатель. Липшиц, значит, просто в первой степени разность. В теории функции есть понятие Липшиц альфа. Я думал, здесь Липшиц М. То есть то, что называют Гёльдером. В уравнениях различает. Я где-то читал отзыв. Это не равенство, то есть не условие Липшица, а условие Гёльдера. В теории функции это одно и то же. Но в дифференциальных уравнениях это разное. Так, Мухаммад, sorry, please continue.
Let's talk first about motivation and some related literature to study this uh, integral. And the setup considered is a geometrically nonlinear analog of Knuffa-Kohn paper from 2011, where the isoperimetric problem for geometrically linear elastic two-phase inclusion problem had been investigated, and our aim is to deduce quantitative information on the nucleation problem by studying its scaling properties. Physically, the problem is motivated by the nucleation phenomena which arise in shape memory materials. And we emphasize that nonlinear models are more general than the linear ones and should be considered primarily.
Sorry, can you show the previous slide? Yeah, this one. This chi is, you say about the interfacial energy. It means that
Yes.
there is two phases, and between those two kinds of materials, and there is a boundary between them, yeah, some surface. And I think maybe chi is one on the one material and equals to zero to another maybe. And there must be some surface if there is interfacial energy. Energy when these two phases or two kinds of material are touching each other. But this, I cannot see any surface. Maybe it will be later or no. You continue the same to talk about that on the same slide too. What does it mean interfacial energy in this case? Interfacial usually is you have two kinds of materials and there is a surface which divides this space into these two kind of materials. And the energy which is coming through this surface is usually phase, or maybe here is in another sense.
It's like
Different meaning.
It's like we look usually, let's take a simple example. For example, quadrat, right?
Yes.
Quadrat. And what will be the interfacial energy? So interfacial energy, then if we calculate this will be just a perimeter of
border of this quadrat. Yeah.
Yes, perimeter of the quadrat.
Yeah. Yeah.
And
but there is R2 because of that. And it means that chi is 1 inside this square and 0 outside this square. Yeah.
Yes, correct.
Something. It means that the M capital, previous slide, M capital must have the smooth, maybe smooth or the smooth boundary, maybe. Ну, или кусочно-гладкую границу должен иметь M. Не просто любое множество. Not any set with measure, with finite measure. Maybe M is not the
So it cannot be very, very
Похоже,
bad.
что M область кусочно-гладкой границы. M is not square in your example?
Yes, we also consider this case later
okay.
on, of course.
Yeah, okay. Yeah, please continue.
Then, physically, the problem is motivated by the nucleation phenomena, which arise, for instance, in shape memory alloys. And we emphasize that nonlinear models are more general than the linear ones, and therefore it should be studied mainly. And linearized elasticity correctly describes only very particular deformations that are chosen to elastic equilibria. And for comparison of these physical phenomena, you can look at this literature 3 for a comparison of the two theories about the linear and geometrically nonlinear theories you can find in the 3. Okay, then let's move on to our problem, and two-well elasticity problem with interfacial energy, and the wells are represented here by the SO2 orbit of the identity matrix and by SO2F, and where F is this is matrix excluding SO2. We also assume that wells are compatible. So what does it mean? It means that there is R from SO2 such that rank R minus F is equals to 1. And since we are considering in 2 dimensions, therefore, by the polar decomposition, this condition will be equivalent to determinant of F equals to 1.
Just a second. Why I don't understand. We assume that the wells are compatible, and there is R such that the rank R minus F equals 1, and this equivalent to the condition that determinant F equals 1. Determinant F, yeah, it has inverse matrix. And R is in general is like F, yeah. In this case, usually rank F is 2, yeah.
Yes, rank of 2.
But rank R minus F is 1.
Yes, rank.
It means you can choose R from this group SO2 such that it can you can change only one part of us, but not it not coincide with the whole F, because F is R2 minus SO2, set minus, yeah, SO2. Так. However, it's possible to choose something R which is near to R, RF. Да. Okay. Please continue.
Okay, then let's take first our result. So this is a theorem scaling of the ground state energy. Suppose that F is from this space which satisfies determinant if is equals to 1 and mu be as in 1, which means the mu is equals to the volume of chi. And let m is this m is bigger than maximum norm of f and f minus 1 plus s for sufficiently large constant c. Then for any mu positive, we have following result, following estimate holds for our energy. Okay, this is chi v is.
Sorry, where is this m?
This m is Lipschitz constant. I mean, this
again the same.
Yeah.
For some sufficiently large constant c, then for any mu greater than 0, we have infimum of this integral, infimum of this integral.
Yeah, this is
approximately mu
1 over 2 and 2 over 3 for m mu less than 1 and mu bigger than 1. And this sign, which is equivalent sign, means this is equals up to some constant which depends on f, but it's independent of mu.
Sorry, I don't understand. Mu is fixed.
Mu is
this equivalency, something like equivalency. Usually it arises when something tends to 0 or to infinity or to some other point. There is no limit, yeah?
no.
What's the meaning of this sign?
This means this is bounded above and below with some
by constant multiplied by mu in this power, yeah?
Yeah. Constant with mu, and constant is independent of this mu.
Так, mu 1 over 2, mu 2 over 3. Так, it's very interesting. Yeah. But on the top, when mu is less than 1, it's not necessary to have estimate above. Only, no, mu in the power 1i. It means that above is when mu tends to 0. The next mu greater than 1, it means that mu tends to infinity. In other case, if mu is bounded from, for example, 1 over 2 till 2, it's nothing. It's not necessary. When mu tends to 0, there is above it. Mu tends to infinity, you use mu in the power 2 or 3. Это же асимптотическое равенство. Оно имеет смысл либо когда mu к нулю стремится, это верхний тогда годится, либо mu когда к бесконечности. Тогда нижняя годится. Нижняя как 2/3, а в нуле как корень из mu. То есть растет медленнее, чем mu при больших mu, но и к нулю идет все-таки не быстрее, чем корень из mu. Так, опять непонятно. Пусть m, let m is greater than maximum norma f. Это всегда же можно сделать. Вот I don't understand only one thing. If m is the Lipschitz constant, any number which is greater than m is the Lipschitz constant too. Also, it's okay, it's correct or no? Again, the question is the following. We consider some function, matrix function, doesn't matter. And M is its Lipschitz constant. Do you understand that? Question, any number which is greater than M is also the Lipschitz constant. Is it correct or no? Because it depends on the definition of Lipschitz constant. Если у вас есть постоянная Липшица, постоянно не в смысле показателя, а в смысле коэффициента перед разностью, то любое число большее, чем это постоянно, тоже постоянная Липшица. Или же постоянная Липшица минимальная. А если минимальная, это очень трудно, потому что в одной точке может достигаться минимум, и с этой точки попробуй возить.
But here there's one thing. This M is also Lipschitz constant for its inverse. It should be
The same. That M1 is for function, M2 is for inverse, and we choose M greater than M1 and M2 and every given number. In this case, is it it will be. You think it's sufficiently large, let M. Yeah, again, there is only one question, which is not concerned with this function, with this presentation. If we have some function, Lipschitz function f, which Lipschitz constant is m, the question is any constant which is greater than m also the Lipschitz constant for this function, or it's not correct?
Знаете, вот еще здесь константа А, вот этот Николай, АМ от М зависит. Может быть, в этом дело, то, что...
Какая А? Здесь нету А.
Вот где этот.
АМ.
АМ, может быть, она...
Can you show AM? Здесь все.
Это множество.
Это целое множество, да? Все, теперь понятно, да, совершенно верно. Все. Теперь понятно. Теперь понятно. Так, again, show this result. Сделаем. Здесь смысл такой, что так, если вы берете функции с достаточно большими константами Липшица, то для них всегда можно получить такую оценку. Так что ли, да? Инфимум берется по всем. Так, если будем m увеличивать, инфимум будет уменьшаться, правильно, да? Если m увеличивать, а m тоже будет увеличиваться, множество. Там все больше и больше функций добавляется. А тогда инфимум, конечно, будет уменьшаться. И вот этот уже достаточно большое множество надо взять. И там минимум. Вот теперь хоть смысл понятен более-менее. То есть вы берете интеграл e от хи v, от e of kind v, да, и берете минимум этого интеграла по всем функциям хи и v из очень большого множества. Если взять из маленького множества, то эта оценка неверная. Нужно взять очень большое множество а. Вот. Тогда, если множество а достаточно большое, тогда этот минимум. А так вы можете минимум, не тот минимум взять. Значит, такой смысл. Итак, снова, если m маленькое взять достаточно большим, то есть существуют такие большие, значит, очень большие, то тогда в них найдется точка минимума, что интеграл будет в этой точке минимума асимптотически μ в степени 1/2. А если же взять m маленькое маленьким, то тогда это неверно, потому что точка минимума окажется за пределами этого множества. Ну, по крайней мере, смысл теперь ясен. Почему net m? Все. Thank you. Please continue.
Next, let's for the upper bound, we can test by taking nabla v, our gradient v is equals to identity, and while chi is which is the ball. I mean, this is support of chi is just a ball-shaped inclusion. Then we can, if we plug in these two values into our integral, and chi and identity, then afterwards for the elastic energy we get that Cf, which is some constant which depends on F, times mu, while for the interfacial energy, this is just I mean perimeter of this ball will be equals to some constant mu 1/2. So what does it mean? It means that if mu is smaller than 1, then surface energy prevails, which means this one. And while if mu is bigger than 1, then elastic energy is dominant. So that means that if from this result, I mean the first upper bound, which is mu 1/3, for mu smaller than 1 is already shown for upper bound case. If mu is bigger than 1, then here it says it's bounded by this one. But we have beta bound, which is 2/3 for mu bigger than 1. Therefore, it remains for upper bound, we have to prove for mu bigger than 1, while mu less than 1 is obvious.
Okay. It's, from mechanical point of view, from the theory of elasticity, it's understandable. Значит, здесь как? Если μ маленькое, то есть размер маленький, почему масло плавает в воде, маленькие шарики? Потому что μ объем маленький, ну, тут двумерный, но если трехмерный, то же самое надо. Когда μ маленькое, поверхностная энергия сильная, она заставляет масло собраться в шарик. И вот эта поверхность держит этот шарик крепко. Если мера очень большая, то этого энергии поверхности не хватает. И в этом случае уже вот это elastic energy размазывает шарики, получается какие-то непонятные там объемы. Вот, странной формы даже масла. Это именно из-за того, что объем оказался больше единицы. Ну, намного больше, наверное, да. И вот как раз граница здесь равна единице. Ну, так, условно, на самом деле здесь асимптотически. Когда стремится, единица наверняка это не есть граница. Просто имеется в виду, что когда, да, μ это размер вот этой капли. Если капля очень маленькая, она будет стягиваться в круг на плоскости, но на поверхности воды или в шарик, если это внутри воды. Но если μ очень большой, то не бывает таких шариков. Превращается в какие-то непонятные фигуры. М большой приобретает какую-то странную форму. Ну, тоже с границей, конечно. В этом случае, да. То есть модель, по-моему, адекватно описывает состояние, в общем-то. Thank you. Please continue.
Then, before we prove the upper bound, we want to recall some of the linear algebra facts, which we remind. If f is from GL2, be positive definite and symmetric with determinant f is equals to 1, then the following result holds. For R from SO2 and U is equals to UT, positive definite, then we have distance RU SO2 is equals to the Frobenius norm of U minus identity. And fact B is there exists R from SO2 and AB from R2 such that F can
U
be...
is a unitary matrix. So,
yes.
the distance RO for R from SO2.
По-моему, не unitary, positive definite.
Транспортированный, что там?
Transpose is equal to...
Положительный матриц, положительная матрица.
У равна транспортированной.
Да.
Да. Так. There exists R, SO2 and AB from such that R плюс... это тензорное произведение, да? АБ.
Yes, it's tensor.
Да, такая матрица. F equals R plus AB from any matrix. It's well known, no? Or B, the result B. Or it's, did you prove it?
Yeah, it's known results. I mean, actually, from linear algebra, we also show in the, our paper as an appendix, because it's
Yeah,
widely
okay.
used.
Фермандер used it very much, very often. У Фермандера в очень многих работах написано, все знают, но нигде не нашел доказательства, поэтому приведу. It's well known, everybody knows it, but I cannot find any quotation in the mathematical literature. Because of that, I'll give the proof. Yeah, okay. Так, C, there exists F ID plus B with B1, 0 from RT such that distance. Okay, some technical, result.
Yes.
Please continue.
Then the last one is we can replace F with F prime, but distance will be the same.
Yeah.
Okay, then with the help of B and C, and we can replace our F for upper bound as an identity plus new tensor product E2 for some nu equals to nu1, 0 in R2. Here in this picture, so what we need to do to prove upper bound. So to prove upper bound, we have to construct a V that gives us this result. So we have to choose one V. So before choosing V, first we identify this helpful function, which is U0. So U0 is equals to F minus identity in this lens-shaped figure. And in the normal direction, these are constant, and other places it's equals to 0. Okay, let's be more precise. So how to choose this U0, and let x1 and x2 be in R2 such that x1 equals to minus x2 on the axis x1 equals to 0, and d is x1 minus x2. And we define chi as the function, a characteristic function of QTR, where QTR is the intersection of two balls with the center x1 and x2 with radius rho. And choose t so that measure of QTR is equals to mu, and in particular we can choose this t to be r times t is equivalent to mu, Then we take U0 such that F minus identity times X in QTR, and outside of QTR, U0 is constant on all lines which are normal to the surface QTR, and finally, U0 is equals to 0 in the remaining area, which is neither in QTR nor reached by any these lines. Okay, then this function is of course not regular enough for us to be V, and therefore we need to identify omega r, which is smooth P cutoff function with omega r is equals to 1 in the ball with radius r, and it's equals to 0 outside of 2r ball with gradient of omega r is smaller than c over r for fixed c, and afterwards we define our v, which is from R2 to R2 by omega r times u0 plus x. Okay, then by the construction of u0, we have that nabla u0 is smaller than 1 for x in this length shaped shape, and t over r for x in not in this length. And further, we have that u0 is bounded by t, and since nabla v equals to f in qtr, and nabla v is equals to identity, and the outside of the wall, we get that our elastic energy is smaller than, which is 1 integral b 2r minus qtr distance squared nabla v SO2 is smaller than up to constant b2r minus qtr nabla v minus identity square. And then this is also, I mean, we can plug in what's the nabla v by its this formula, and then we get by simple calculations these two integrals. Then nabla v is bounded by 1 over r and u is bounded by t. Therefore, first, this norm is bounded by t over r squared. While the second one, nabla u0, this is outside of this set. Therefore, this is also bounded by t over r squared. And then, since Tr is equivalent to mu and also including the interfacial part of the energy, we obtain that this energy is smaller than the perimeter of this length plus t squared or r squared, and then this first one is then bounded by r, which is perimeter of this length, and plus t squared. So then afterwards, we have r plus mu squared or r squared, because t times r is equivalent to mu, and the choice of r equivalent to mu 2 over 3 minimizes the last term by mu to the power of 2 over 3. So this gives us the upper bound.
Please, just a second. Mu square r plus r square r in the power 2 over 3, 4. It's 4 over 3 is 2, yes. 2, the 4 over 3 is power mu in the power square. Square. Just 2 over 3 in mu. R square, я? Значит, 4 третьих. Квадрат 2 минус 4 третьих. Сколько будет? 2 третьих, да? Да, точно. It's a minimum. It's a real minimum. Yeah? Yeah. Just when R equals to this mu square over R square. It means R cube equals mu square, okay? On the right-hand side, two terms are equal one to another. And because of that, this power 2 or 3. Okay, please continue.
Okay, then we have the upper bound. What's remaining is that we have to show that this R belongs to this admissible set. So chi and v is actually from admissible set. Then we are showing
It was necessary to have very big Lipschitz constant, yeah, in this proof.
Yes.
It doesn't matter what is the Lipschitz constant. Okay. And R plus t square, it means some constant with R and some constant with t square, no?
This is depend on some constant, yeah, because we have tweeted.
Not R plus t square, C1R plus C2 t square. It's not so.
We can choose the maximum of this constant and
yeah, doesn't matter. Yeah, okay.
It doesn't because we are not very precise on this.
It's less than constant multiplied by R plus t square.
Yes.
Yeah, correct. Not just is this constant is not necessary. It is to be equal to 1.
Yeah, it's not necessary. Yes, to be 1, but
it means that its inequality is not strictly correct. You need to add the c and R plus t square in brackets, but it doesn't matter for minimum.
Yes, we can always pull out these constants. I mean,
yeah, and it doesn't matter for minimum because it's R plus t square in brackets.
Yes.
Inside. Okay. Now please continue.
And then admissibility of this chi and v is actually from this space. We are proving it here, and the first of all is chi is from BV R2 0 1, and nabla V is bounded by CF, and let B1 and B2 be for X B2R excluding QTR be positive oriented basis, where B2 is the direction of the lines in B2R minus QTR, where U is a constant, and B2x times E2 is bigger than 0. And we also choose that B1x minus EI is smaller than capital O T or R for I equals to 1 and 2. And since nabla U0 x times B2x is equal to 0, we get that nabla U0 E2 is smaller than C times norm of F T divided by R. And since F minus identity E1 is equals to 0, and this is just upper triangular matrix and times E1, and we also have that nabla U0 B1 is smaller than this constant times T over R. So together this implies that nabla U is smaller than C times T over R, and since nabla V omega R is bounded by 1 and nabla omega R is smaller than 1 over R, this implies that this expression, this bound holds. Then we have that, I mean, we can replace this term by nabla V minus identity because it's equals to this, and then this is smaller than C times 1 plus T over R, and then this is also smaller than c times norm of f mu to the power of minus 1 over 3. So then, as a consequence of the Neumann series, arguments implies that it's the inverse of the nabla v x is also bounded by some c times norm of f for sufficiently large R. So then, assuming now we showed what we have showed, I mean, nabla v is bounded and nabla v minus 1 is also bounded. Now what remains to show it's v is injective. So we want to show that v is also invertible. So assume that Vx is equals to Vy for some x and y in R2. So after using the fundamental theorem of the calculus, so we get that 0, 1 nabla v tx plus 1 minus ty dt and times x minus 1 is equals to 0. So nabla v is the perturbation of a upper triangular matrix. Therefore, first bracket cannot be 0. Therefore, it implies that x minus y is equal to 0. So this proves the injectivity of the v. So we have shown that v and chi, this pair is admissible. So we have showed the upper bound here.
Yeah.
Okay, next, the lower bound. For lower bound, we need following result. First, let R is positive and chi is from this set. And then there is nu positive such that the following holds. Suppose that chi and v is from this admissible set and satisfies that chi volume of chi is smaller than nu times r squared and perimeter of the chi is smaller than nu times r. Then their constant alpha, which depends on m from 0, 1, and c, which depends on f, alpha, and m, such that elastic energy is bounded below by c over r squared volume of chi v squared. Then, so let's give a strategy of the proving the lower bound. This is the first. This theorem is a variant of the result by Conti and Schweitzer 2006 on the two-way rigidity. Okay, they stated the similar result, but what we have had here is we just adjusted the result to our situation. And next, what we do is we apply the arguments of the Knuffe-Kohn 2011, which this result for the geometrically linear result, we are applying the result for the nonlinear result, which our result implies the lower bound. Okay, let's go to the, this is a proof strategy. So first, we argue by localization and the covering arguments. We consider the suitable chosen countable family of the balls B Ri Xi covering the support of chi, and by Vitali covering lemma, since Ri is uniformly bounded, we may assume that B Ri over 5 Xi are pairwise disjoint. Then we can localize the energy as follows. So energy is bounded below by the sum of I equals to 1 to infinity energy with a ball Ri over 5 xi, where this sign, this E means that this is the energy with chi V B Ri xi. This is a ball with a radius Ri and xi. Now, if we would bound E Ri over 5 xi from below in terms of the M intersection with B Ri xi to the power of 2 over 3, we could conclude their argument because this would be energy bounded by the sum of these things, and this is also bounded by this, and this energy is smaller than mu to the power of 2 over 3, depending on some constant, and therefore it remains to prove that epsilon E Ri over 5 xi is smaller than M intersection with BRI xi to the power of 2 over 3. So we need to show this thing in order to prove the lower bound. So for this, we split into two claims. So this we have to prove. So so that means that it's equivalent to prove the following two inequalities. So first one is M intersection with B alpha Ri over 5 xi is bounded below by M intersection with BRI xi, and while the energy over Ri over 5 xi is bounded by M intersection with B alpha Ri over 5 xi to the power of 2 over 3. Suitably chosen balls B Ri xi, we note that all the estimates in this proof may depend on the constant alpha. Okay, how do you show these two inequalities? So for first, for x in M and nu small, we first set that Rx is equals to infimum R to the power of -2, M intersection Brx smaller than nu 0, and minimum 1, and this measure. Then if R tends to 0, then R to the power of -2, the measure M intersection with Brx is smaller than nu 0. This inequality is not satisfied for x with density 1. If R goes to infinity, then we search for the largest R positive, satisfying mu over R squared smaller than eta 0, mu to the power of -1 over 3. Hence, there is R which is smaller than this bound, and either M, this first one satisfied, or the second one is satisfied. First one, if it's smaller than 1, then this minimum is equals to 1. Therefore, we obtain this thing. If this is, so we are splitting into 2. So if this is less than 1, then we have here as a minimum 1. Then we have this one. If this one is bigger than 1, then we have the minimum as this term, which is M intersection with BR to the power of 1 over 3. So next, we consider the three cases. So by the definition of R, we obtain the following statements. If this measure is smaller than 1, and this measure with alpha r to the 5 is also smaller than 1. Then we obtain this inequality. So next case is both of these terms are bigger than 1. If both of these terms measures are bigger than 1, then we obtain this inequality. So finally, if this term is smaller than 1 and this term is bigger than 1, then we have this inequality holds. Okay, then let's say M intersection with B.
Just a second. This is yeah. If M intersection with B alpha RE over 5 less than 1, another M is greater than 1, then M in the denominator greater than eta 0. Why? I don't understand. M alpha in the power 4 over 3, it's okay, but this is in the power 1 on the left side. It's less than, or it's less than 1, yeah? Less than 1, it's greater than in the power 4 over 3. Because it's less than 1. Так, сейчас x, когда меньше единицы, то он меньше, чем x в степени 4 третьих. Больше, да, больше. Если степень увеличивается, число уменьшается. Yeah, it's okay, yeah. But last, it's M intersection is it's greater than 1. Да, yeah, it's okay. No questions, please.
Yeah, alpha is between 0 and 1 also.
Yes, because it's 1 is between these two measures, yeah. Only because of that. Если число меньше единицы, то увеличите степень, оно уменьшится. А если число больше единицы, то увеличите степень, оно увеличится. Вот
Но
это
они
здесь
же
есть.
оба больше единицы. Если по одному...
Нет, слева там оно меньше единицы же, да?
То, что в числителе находится.
Да, числитель меньше единицы, поэтому если бы он был это первой степени больше, чем в степени 4 третьих. А 4 третьих больше, чем числитель в правой дроби 4 третьих, а та больше, чем в первой степени.
То, что в знаменателе. А то, что в числителе, они же они оба просто меньше единицы, то есть между ними же нет никакого неравенства.
Нет, почему? Там, видите, выше написано, что числитель в правой, он больше единицы.
Нет, они оба меньше единицы, у меня написано, вот здесь.
Он считает, finally, if m is less than 1, а вот это m больше, чем 1. Выше написано, наконец, если...
Да, это в последнем, а вот в первом они...
Первый, меня вот последнее привлекло внимание, поэтому я смотрю. А первое сейчас, если они оба меньше единицы, да, то
Мы
тогда...
не можем сравнивать таким образом. Если других сведений, как бы другой информации нет, наверное, мы можем так сравнивать, что одно больше.
Там, видно, со знаменателем связано. Предыдущее там должно быть. Альфа R, наверное, это раньше использовалось, нет?
Может быть, да.
Why the upper inequality is correct? Intersection M B alpha RE greater than intersection M B R without alpha.
Там надо альфа посмотреть, что такое альфа.
Yes, this is...
Где альфа? Сейчас.
Вот в том неравенстве, о котором вы
Да-да-да,
говорили.
там есть, но
Перейдите
альфа...
на следующий. Вот, смотрите, тут
Да, но
все зависит от альфа.
вот из альфа here. Так, R и T поделить на 5. Это число альфа какое, да?
Alpha is between 0 and 1.
Так, видно, вот эта дробь, она Alpha is between 0 and 1.
Yes.
Эта дробь растет, когда альфа уменьшается. Вот так получается. Справа, когда альфа равно единице. On the right hand side,
Нет, там еще пятерка есть. Там еще пятерка есть.
есть пятерка. Не, какая разница? В числителе тоже есть пятерка.
По-моему,
вместо
это
альфа-
по определению RI это инфимум вот этот самый.
Да,
По определению.
вместо альфа возьмите альфа, деленное на 5. И вот это, оно меньше единицы по условию. Альфа меньше 5.
Нет, вот это меньше, чем RI получается, да? А там инфимум берется.
Ну
А
да.
если чуть меньше возьмем, тогда это обратное неравенство выполняется, по-моему.
Если вы уменьшаете, то инфимум становится больше.
Нет, вот там определение RI, там
Ну да, так
предыдущий слайд.
поэтому будет справедливо это неравенство. Потому что множество, по которым берется альфа, уменьшается, значит инфимум больше, поэтому левая часть больше, чем правая.
Ну,
Да,
а
да,
то,
да.
что оба числителя меньше единицы, это не влияет на это. То есть это не зависит от того, что они оба меньше.
Нет. Это просто тут надо было так написать. В первом случае мы воспользуемся следующим очевидным неравенством. А во втором случае, мы просто 3 случая рассматриваем.
Да.
Во втором случае мы воспользуемся вот таким неравенством, да. И когда больше единицы, тогда в степени 4/3. Когда оба больше единицы. Там то же самое. Сейчас. 4/3 это больше единицы. Второй случай сомнения может быть. Когда они оба больше единицы, то альфа и поделить на 5 в степени 4/3. Почему это больше, чем справа? Bu kayadan çıkmadı ikincisi. How can you prove the second inequality? Так.
If it's bigger than
Why?
1. If it's bigger than 1, then we have mu intersection with BRX is equals to nu 0, m intersection with BRX to the power of -1/3 times r squared.
Там
So
нужно еще более детально предыдущее смотреть.
this is,
Yes. Okay. Please continue.
and then for this term, then it will be equals to nu. Then this
Yeah.
is true.
Yeah. The last is understandable. Okay, please.
Okay, then
Further.
let's say mu now we look at the first case, which is m intersection with br is smaller than 1, and mu intersection with brx is equals to nu 0 r squared. And then for this case is we get by the use of the isoperimetric inequality this perimeter on this ball is smaller than m intersection with BRI.
Bigger than.
Yeah, bigger than 1 over with the power 1 over 2, because it was d minus 1 over d. So d minus 1, this isoperimetric inequality. Then this is equivalent to m intersection with BRI xi to the power of 1 over 3. And this is, since this thing is smaller than 1, we have that this is bigger than m intersection with BRI xi to the power of 2 over 3. So this case has been, is proved. So the next we split into, we consider other case, which is m intersection with
I
BRI.
see analogously, yeah, the same proof, yeah. And the final result, which is the final result.
So
Is the end of the proof of theorem. Is it okay?
Then we are also looking at this case, which is integral is also bigger than Ri holds. Yeah. Then we have also the simple proof.
Yeah, okay.
Simple lower bound. Then next one is we are, since putting this condition.
Подождать, уже
Да.
время вышло. Может быть, Ибрахимбек, он покажет самый последний слайд, как это все получилось.
Yes, this is the last slide then. Then we
Okay.
consider the
Это и
case.
есть последний слайд.
Yes, this is last slide. If it's bigger and the integral is now smaller than Ri. So this estimate requires a small universal constant. Then here we can choose eta 0 small
Okay.
enough so that assumption of the theorem.
Okay, you see, it's a very interesting result. I can say honestly, I never see such a condition that the Lipschitz constant must be greater than 1 or greater than something. Never. Usually, and because of that, I think it would be very useful if you check this proof again with very carefully. It's really necessary for you to demand that Lipschitz constant must be greater than 1. Maybe it's enough just to have the Lipschitz constant, that's all. Yeah, okay, because I cannot find the moment when you are using this condition. The Lipschitz constant must be greater than 1. Must be a big number. Yeah, because if there exists any number which is greater, it's okay. It's just the same constant. Yeah. However, some more questions or some suggestions maybe or discussions. Какие-то есть вопросы, может быть, или что-то вызвало какое-то еще требует разъяснения, может быть, что-нибудь. Вообще доклад немножко превысил наше стандартное время, да? Вот.
Да,
Хотя
да.
обычно доклады 1,5 часа продолжались раньше, не помню. Сейчас новые времена, сейчас все идет быстрее. Вот. Хотя нет, вы знаете, 1,5 часа с интервалом, с перерывом, вот на семинаре, итого 90 минут, да, вот на семинаре Меньшова и Ульянова, да и на других семинарах перерыв никогда не был 15 минут. Он был как минимум полчаса, а может быть и больше. Потому что во время перерыва как раз больше всего дискуссий было. Так, ладно. Если нет вопросов, no question, no. Да. Раз нет вопросов, тогда позвольте поблагодарить доклад. Мне кажется, этот доклад был очень интересный, и сама задача очень интересная. Вот, потому что действительно это возникают практически важные вопросы, связанные именно с образованием вот этих вот капель. Да. Они идут в самых разных реакциях. Почему они имеют именно такую форму? И в какой момент они все-таки существуют, и в какой момент они распадаются, и начинается другая реакция. Это механика, но она тесно связана еще и с химией, конечно, да. Сейчас трудно предугадать, где это может быть использовано. Да. Тогда позвольте поблагодарить докладчика Сузгемина Дочерьевна Бальдамовщина. Ну, и она намается вот это. Thank you very much in English language for a very interesting presentation. Да. Қайсы тілде яна қош мүмкін? Ваша Раджапович. Yeterli mi?